All right. This is the third part of our week 6 discussion. So, as I promised, I will email you the subscale, but I really looked at the SRC data again, and there were 853 participants in the raw data. And then I've looked at my publication of the acceptability E-scale, and there were 627 in the final data analysis. So that would make sense that perhaps the statistician who ran the exploratory factor analysis did clean up this 853 and only included 624. And that explains why I'm getting a different result. So that's me. I always try to make sense of everything. I was like, oh my goodness, is this for real? This doesn't make sense. So, all right. I have a little bit of peace of mind now that definitely what I'm running is a very different data set with 800. This data set right now shows that there's 853, and my final, the one that the statistician gave me, was only 627 participants. So that's more than 200 participants. That's more than 200 in the discrepancy in the N, or the sample size. So, okay, but I do promise you that I will run those 3 based on the technology acceptance model by Dr. Fred Davis. The perceived usefulness, which is the satisfaction subscale, and then the ease of use, which is the usability subscale that the French actually published in their study in psychiatric patient population. All right, so that's the last step of exploratory factor analysis, is to run Cronbach's alpha of each subscale that the entire item bank created. So in my current study, I have 22 items in my bank. I will check what would be the parallel analysis, which is now the accepted or the standard for determining how many factors will be retained. In the old days, it was the eigenvalue of 1 or greater that determines the number of factors, or what we call the construct of your full model. So, all right, let's change gear now to even more challenging one. It's the structural equation modeling. I almost did a structural equation modeling in my PhD study at the University of Washington, because when I did an analysis on decision making, I had a nice conceptual map, or what we call the conceptual framework, and I really thought that structural equation modeling would be the right statistics for my dissertation at that time, because I had a very complex representation of decision satisfaction and quality of life as an outcome of 3 main factors, which are the patient factor, the physician factor, and the systems factor. So I was entertaining about structural equation modeling, but I ended up not doing this. I ended up actually, my final dissertation was a mixed model. I had a qualitative part of my dissertation where I interviewed 20 multiple myeloma patients, and I examined the patient factor, the physician factor, and the systems factor. And then I had the quantitative aspect of it where I used the control preferences scale by Dr. Digner, who is Canadian and who actually is retired now. And I had the extreme chance of meeting her during the annual Oncology Nursing Society, where she was invited as the distinguished research lecturer. And boy, did I really sort of like aggressively go to the stage after her presentation. I introduced myself. I said, hey, hi, Dr. Digner. I'm a PhD student and I use your tool, the control preferences scale, in my dissertation study. So that's really a very good story there. So in my dissertation, I used a mixed model, and this mixed model used a qualitative, and I utilized the coding method of in vivo, which is a qualitative software for qualitative data research type. And then I've used the control preferences scale for my quantitative aspect of my dissertation, which look at only the patient factor, which is the what are the preferences, what are the level of preferences of patient in cancer treatment decision making when they are diagnosed with multiple myeloma. So in the quantitative aspect of my dissertation, there was definitely the two other factors in my conceptual framework were not measured, and it's still an area of interest for me. As I get older, I'm looking for sophisticated models and sophisticated determinants for my outcome of decision satisfaction. And I wanted to really simultaneously and quantitatively examine the patient factor, the physician factor, and then the systems factor. And one of the drivers why I'm very passionate about developing the shared decision-making scale for nurses is that I strongly believe that nurses are not just bystander in cancer treatment decision-making. And so in my thinking, if I can't measure the nurses' participation and nurses' competence in shared decision-making, I won't be able to plug that into my my model of what I think are important determinants to patients' decision satisfaction and patients' overall quality of life. So this is really can be traced back way back when I was still a PhD student. So this is what you call a lifetime commitment to expand the science in your field of interest. All right, so let's talk about structural equation modeling. Here's the overview. Structural equation modeling describes the types of research question that can be addressed. It identifies data set requirements and describes relationship between the measurement model and the theoretical model. So there's two models that are simultaneously examined in structural equation modeling. You have the measurement model and the theoretical model. This is quite a very complex statistical method, and you really need an expert. Miss, palayo ko mute sa microphone. Palayo ko mute sa mo microphone just so we won't capture the conversation. Okay, thank you. And so structural equation modeling describe the role of the theory in the structural equation modeling process. And one of the critique of structural equation modeling analysis is on the basis of the model fit statistics. And I will try to explain this a little bit more in a little bit. So structural equation modeling, like path analysis, is used when you want to test theoretical models depicting relationship between concepts. So the way I look at structural modeling is really very, very, this is looking at covariances. So it's important to look at your data, and if you're looking at ANCOVA, which is analysis of covariance, and if there is existence of covariances, then it's important to look at potential application of SEM. SEM has been referred to as latent variable analysis. So that's the analysis of the relationship between latent variables. So just like exploratory factor analysis, in exploratory factor analysis, it also look at those latent variables. So the one that we don't see right away, these are the abstract variable or abstract constructs. And we try to make sense of them later, and that's why it's called latent variables. And these are the unmeasurable constructs. So the name LISREL was the name for the first software available for conducting SEM. So that's why it's also called the LISREL analysis, which is latent variable analysis, a way of analyzing all the items in your tool. So SEM challenges us to think about how we measure theoretical construct. It allows us to do a lot of simultaneous use of multiple measures of theoretical constructs. And a very good example that's given by the textbook is that researchers do not have to settle for one measure of health. We can look at health as a psychological, as a performance, as a physiologic measure, and the response options of this measure can vary depending on the measure that you use. So instead of using health attitude questionnaire, you can also use looking at what's the total item responses into one lump sum or one scale. And each item can be treated as a separate measure of health. So let's, we should ask Agnes to mute her microphone because I think Agnes has the unmute microphone. Can you text Agnes Palihog? So ma-mute niya ang microphone. Maybe I can send her a message. Let's take a look. Okay, thanks. All right, so SEM measures two models simultaneously. So this this is the difference, one of the key differences of structural equation modeling from exploratory factor analysis. When you do exploratory factor analysis, you do have a theory in mind, and you do have a conceptual framework in mind. And then you develop all of your items based on the conceptual framework that you have done prior to item development. So that's in the exploratory factor analysis. It's very useful in tool development, in assessing how many factors are present in a scale. So in structural equation modeling, what's different here is that you actually have the tools already. You are using valid and reliable tool that measures all the construct that you think are part of your theoretical construct. So that's the major difference here. In structural equation modeling, you are not developing a tool. You are not testing validity and reliability of the tool. You already have a theory, and these different constructs of the theory are measurable by a valid and reliable scale already. So I hope that this is very clear that we cannot do structural equation modeling if we don't have the scale that can measure the construct in your theoretical construct. So SEM is an advanced statistical analysis that require that all of the constructs are already measurable by a valid and reliable tool. Exploratory factor analysis, you are trying to develop the tool to measure this construct. So that's really very important. So this is the reason why I back out on doing structural equation modeling for my dissertation, because I realize I don't have a tool to measure the system factors that will influence the decision satisfaction of multiple myeloma patients. There is already a tool to measure patient factors, such as the control preference scale that Dr. Digner developed. And then we also have a lot of tool that would measure the physician factor, which is developed by a lot of decision scientists, and it's very complex to measure physician factors because it's based on a two observer, and the reliability has to, it's called the kappa coefficient, where the scoring of the physician factors are consistently reliable. And in my original model, I was thinking, how am I going to measure the system's factor? And if I don't have that tool yet. And I said, okay, I have the tool to measure patient factor. I have the tool to measure the physician factor, but it's very complex because it needs two observer in the actual clinic, and there has to be consistency and reliability of the scoring of the two observer for the physician factor. So I back out because structural equation modeling is an advanced statistical analysis that will measure simultaneously a measurement model and a theoretical model. And so if your theoretical model have at least 4 constructs, you really have to have valid and reliable tool already that can measure those 4 constructs in your hypothesized theoretical model. So that's really the main difference. You cannot do structural equation modeling if you cannot measure, or if there's no existing valid and reliable tool to measure the construct in your theoretical model. We can break the research question addressed by SEM into 4 categories. The first category is testing the theoretical models. So we will actually cover next week, which is the last part of our statistics 2, is path analysis. So like path analysis, structural equation modeling can be used to test causal relationships. So it's very important that this is a cause and effect. And when we write our model in social science or in nursing science, straight line means it's a cause and effect. If it's not a straight line, it's an association. So there's a proper way of drawing or illustrating your theoretical models by using a straight line or by using a sort of like not a straight line, which is just using spaces between, not to use a straight arrow line, but use the break lines. So structural equation modeling is really going to test cause and effect. So it has similarity with path analysis. Is factor A, the occurrence of factor A leads directly to factor B. So that's what you call causal relationship or causal modeling. Don't be confused with casual, because there's a lot of errors in that. Students always say casual relationship. No, it's cause. It's causal modeling, which is cause and effect. In the way you draw your model is that if factor A happens, this will lead to factor B. So it's really clear that in order for factor B to happen, factor A has to happen first. So that's a very important category of structural equation modeling. However, unlike path analysis, measurement error in structural equation modeling is estimated and removed from the relationships between theoretical constructs. So hold on to this important thought. And then the last of the first category is that structural equation modeling can be used to analyze non-recursive models, which means that exactly means that the models, these are models with two-way paths. So if you have factor A, and factor A can cause factor B and factor C, it's non-recursive for structural equation modeling, which it is able to analyze two paths, but it's based on cause and effect. I think there's a good diagram on this one later on. So just remember that structural equation modeling is non-recursive, and one factor can be the cause for the effect of factor C and factor D. So that's the non-recursive category. The second category for structural equation modeling is it provides a new way to examine the factor structure of an instrument because it allows the assigning of the items to specific factor, and it will load to one more than one factor. And think about this, factor is really construct, okay? So it can be interchangeably used here. When I say factor, it really means the construct that's being measured by the instrument. And then it identifies which items load on more than one factor or one construct, and specifying which factors are or are not correlated with one another. Because the job of structural equation modeling is to look at covariances. So that's one of the major underpinnings of structural equation modeling is that it's covariance of major constructs, or what we call the concept or the constructs that being measured by your instrument that you administer to your respondents. And I'll show that to you in a little bit because this is really, really quite fascinating. I was so like gung-ho about structural equation modeling when I was doing my PhD program because I was so in love with this statistical method or statistical analysis, because can you imagine you'll be able to give 5 or 6 questionnaires that measure 6 different constructs, and these constructs are simultaneously examined as a covariance, and then you already have a theory about how this different constructs that's measured by different instrument is going to have a cause and effect relationship. It was really, really, I was so fascinated by this, but the reason why I back out in doing structural equation modeling when I was doing a PhD was that I didn't have the instrument or the questionnaire that would measure the systems factor. And so as a scientist now, I'm really looking at how do I move the science of decision making, looking at the simultaneous construct, the construct of the patient factor, the constructs of physician factor, the constructs of systems factor, and then you examine them simultaneously, and then you look at how all these constructs exist in a cause and effect underpinning. It's really quite fascinating. So this is the second category. It's a new way to examine factor structure of an instrument because it allows assigning of the item specific to factors, and model fit statistics can then be used to determine how well this factor structure will fit the data, and the fit of alternative factor structures can also be compared. So really, really quite sophisticated statistical analysis. The third category in structural equation modeling is that it provides new way to look at group differences. It compares the magnitude of the different factor loadings, and we can determine if the same theoretical model works equally well for explaining the data in different sample subgroups. These are now the science of structural equation modeling. These are the underpinnings of structural equation modeling. Structural equation modeling opens the door to new questions. For example, with SEM, is it possible to first, it is possible to first to assume, that's my 10-minute warning, to assume that different levels of measurement error are present in data, and then to test the effect of these different levels on the theoretical relationship specified in your original model. So lots and lots of very intellectual curiosity here when you do structural equation modeling. And conclusions can be made about how robust this relationship to the problem, such as poor memories, tendency to alter responses. In the example in the textbook is really quite fascinating. It looks at condom use among HIV patients, so really fascinating. So structural equation modeling, these are the different terminology. I will send this to you as to an email this, so you can review what are indicators, what are measured variables, what are proxies, and what we call the manifest variables. These are different names or terms that refer to the same thing. It's the theoretical construct. And then the residuals and measurement errors are the terms used to refer to the imprecision that's inherent to some extent of any of the instrument that you use. So look at this. This is the measurement model, for example. You have health, you have well-being, and you look at the arrow. If they are straight line, that means cause and effect. So that's a very technical way of illustrating your model. Is when you use straight line arrows, it really means that it's a cause and effect. So that means that A has to happen first before B will happen. So this is a very good example of a measurement model of how theoretical constructs are measured. And theoretical constructs are often called the unmeasured or the latent variables because they are not measured directly by the researcher. Example of that are health in the previous measurement model. They are free of random or systematic measurement error because these are latent construct that you will uncover as a researcher. So they are not subject to random or systematic measurement error. The disturbance is the term in SEM that refers to the error in the prediction of an endogenous latent variable by other latent variables in the model. So these are layers and layers of different concepts. It's analogous to the error variance in linear regression analysis. And the SEM diagram will be designated by a short arrow pointing to the endogenous latent variable. So look at this. So right here is cause and effect. Your health attitudes will result to health behaviors and will lead to your health. So this is really what's very attractive in structural equation modeling, is that you have straight lines that represents cause and effect. And health attitude is going to lead to health behaviors, and health behaviors will lead to health. And then it examines the other endogenous variables, and that could be the age, and there's also that direct cause and effect relationship of age and health. So it's really, really fascinating to use structural equation modeling, but I have to admit that I haven't used this in any of my research. The parameters are often referred to as fixed or free. A fixed parameter, for example, is when you assign a particular value, whereas a free parameter is estimated in the structural equation analysis, and the computer calculates the value as part of the analysis. And it's using this covariance, like in ANCOVA, it has a covariance coefficient. So from SEM, you will get the various model fit statistics, the parameter estimates, and then you also get statistics predicting the potential change in the model fit used by way of the chi-square mathematics. So SEM requires data to have three characteristics. It should be continuous and normally distributed. It should contain indicators of latent variables, and the data should be numerous. That means that SEM requires a large sample size of an N greater than 500. So where do you find that? How do you collect that? And so that's one of the reasons why I backed out in doing SEM in my PhD study, because it's very hard to recruit 500 patients or more in this study. And again, you need to have actual questionnaires already that will measure the construct in your theoretical model in structural equation modeling. So three types of assumption that must be considered with SEM. With SEM is your theoretical, general statistical, and estimation method specific. So these are very heavy in theories. With SEM, assumption of causation are made regarding both measurement of latent variables. And then assumptions are made when paths are drawn. So you really have to have path analysis, and it has to have cause and effect relationship. As I mentioned, factor A will lead to factor B. So you cannot say that B happens by chance. It really has a direct cause and effect relationship. So A has to happen first before B will happen. So that's a very important underpinnings of structural equation analysis. It has similarities with path analysis. It is important to consider the three conditions of causation, so the cause and effect, that there is a presence of an observed and measurable relationship between variables. There is temporal ordering, so that means that temporal means timing. There's, one has to happen first before the other will happen. And then the third conditions of cause and effect. So these are very important, three important concepts in cause and effect relationship in scientific inquiry. Number one, observable and measurable relationship between variables. Number two is temporal ordering. So there has to be A has to happen first before B will happen, and B has to happen first before C will happen, and then C has to happen first before D will happen. That's what you call the temporal ordering of cause and effect. Non-spuriousness means that it's not by error. There is no room for error. It's cannot be spurious. It cannot be a false data, a false assumption. So these are the three major concepts of cause and effect relationship that SEM will analyze. General statistical assumption, there are three assumptions are necessary for linear regression. There's the normal distribution, homoscedasticity, and linear relationship. Assumptions regarding the error terms in the SEM are similar to those for regression. That means that the error terms in the model are not correlated, but covariance is important. There has to be the existence of covariance of the major constructs that's being measured in your SEM. And it is assumed that the sample is asymptotic. So it really means that so large as to almost approaching to infinity. Then there's the third one is the estimation method, which is the specific statistical assumption. And that is, it uses the maximum likelihood mathematics again. I think I'm running out of time. So we will continue. When I run out of time, we will just continue next week. In this example in the textbook is that it's testing a theoretical model of condom use for African-American men with a partner that they know well. And then it's really amazing. Look how complex this theoretical model is. It has all this component, interpersonal consequences, aids communication, aids concern, embarrassment, pleasure, and then it look at alcohol use, it look at the age of the patient, and look at all this a relationship. And remember, it's the underpinning is cause and effect. And